Good day. Uh, Today we will talk about the AC analysis, chapter 3. Um, we should ability to understand and apply the concept of a sinusoid, phasor, and its application in the AC circuit. So the outline is we will talk about the sinusoidal, the phasor relationship for circuit elements, impedance, impedance combination, instantaneous and average power, effective RMS value, apparent power, and power factor. In a sinusoidal, historically, DC sources were the main means of providing electrical power until the late 1800s. At the end of this century, the battle of the direct current versus alternating current began. And because AC is more efficient and economical to transmit over long distances, so AC system end up the winner. We now begin the analysis of the circuits in which the source voltage or current is time varying. We are particularly interested in a sinusoidally time varying excitation, or simply excited by a sinusoidal. A sinusoid is a signal that has the form of the sine and cosine function. So a sinusoidal current is usually referred as an alternating current. We have a positive, we have a negative. So AC. And the circuits driven by the sinusoidal current or voltage sources are called as AC circuits. Also, still remember in the chapter 2 or 1, we have an AC source that connected to the passive element. So if this source driven by the sinusoidal current or a voltage source, then we call as everything will be called as AC circuits. Reason of an interest in the sinusoid is the nature itself is characteristic sinusoidal. And the sinusoidal signal is easy to generate and transmit to homes, factories, laboratories. Through Fourier analysis, and any particular periodic signal can be represented by a sum of a sinusoidal, and easy to be handled in mathematics. So first of all, sinusoidal. What is that? So let's take an example. The sinusoidal voltage Vt equals to Vm sine omega t. Mathematics, actually, it is a mathematics. So Vm is the amplitude of the sinusoidal, means a peak from here to the Vm. This is a peak amplitude. And then omega is the angular frequency of the radian. So we can see that it shifts from a positive plane and a negative plane and positive plane and negative plane. Actually, it has a frequency. So we call it as a frequency. And we have two types of frequency. One is the angular frequency in the radian per second, omega, and then one is f in hertz. So t is called the period of the sinusoidal. It can be equated by omega t equals to 2 pi, whereby omega t means 1 cycle in 2 pi. Pi is a radian, or in electrical degree it is a 360 degree. So we have this equation where t equals to 2 pi over omega. The period t of the periodic function is the time of one complete cycle or the number of seconds per cycle. So for example, if let's say this is one second, from this point until here, it is 1 second. So this is called 1 cycle. Cyclic frequency f of the sinusoidal is reciprocal of the t. We call it as f equals to 1 over t. And then related to omega, which is become omega equals to 2 pi f. So for example, this is 2 pi, then this will be a t, or the period. So in the more general expression for sinusoid, just now we have a Vt equals to Vm sine omega t. We actually can express in a general expression Vt equals to Vm sine omega t plus phi. Vm, peak, from this point until here we call peak. Sine omega t is a waveform of the function. Omega, how frequent it turns. T is it changes according to the time. Maybe time like this, what is the amplitude? For example, time like this, the amplitude is like this. Time like this, the magnitude is like this. Time like this, the magnitude is like this. So from here is positive, it is negative. So omega t is the plus phi. Phi is the displacement from the 0 point. So omega t plus phi is the argument, and phi is a phase. Both argument and phase can be in the radians of degree. It's just a matter of the unit difference. radian or degree, we can do the conversion, no? So for example, my V1t here, no, it is Vm sine omega t. And then I also can express V2t, which is a Vm equals to sine omega t plus phi, like this. So the waveform has shifted back. Okay? When we talk about sinusoid, two things is very frequently used. One is a sine wave, one is a cos wave. But the problem is sometimes you want to change it, interchange it. Or sometimes you want to interchange it. For example, a graphical means of relating cosine and sine wave. From A, this one, cosine omega t minus 90, cosine omega t minus 90, I can get a positive sine omega t. We can try to use calculator to verify this one. Or we look at the B. If I have a sine omega t plus 180 or plus 180, first I have a sine omega t plus 180, then I have a negative sine omega t. So this is how we have an interchange of a cosine function to the sine function. And then we also can add up. For example, I want to adding the A cosine omega t and B sine omega t. So A cosine omega t and B sine omega t, I add it, we have a C vector. We also can add 3 cos omega t and negative 4 sine omega t. So 3 cos omega t, this is x-axis of cos omega t, 3 cos omega t minus sine omega t is here. So I have a vector like this. So this is how we adding or subtracting, subtracting the so-called sine and cosine function. For example, so let's find the amplitude, phase period, and frequency of the sinusoidal. For example, we have a Vt equals to 12 cos 50t plus 10 degree volts. So the amplitude of Vm is a Vm, which is a 12 volt. This is amplitude, this is the big value. Phase is a 10 degree. The angular frequency omega is a 50 radian per second, this one. And then the period t equals to 2 pi omega, which is equals to 2 pi over 50. 50 is omega. And then we have a 0.1257 second as the period. And then the frequency is equals to 1 over time t, which is 7.958 hertz. So calculate example 9.2. Calculate the phase angle between V1, which is negative 10 cos omega t plus 50, and V2 equals to 12 sine omega t minus 10. Which we need to find which function is leading. So when we want to do the comparison, it must be apple to apple. So first of all, we found that V1 is in cosine, V2 is in sine. So what we need to do is we need to turn one of it become either cosine, either sine. So in this example, we turn V1, we convert V1 to, we will convert V2 to cosine function. So first of all, we need to make sure everything will be in positive amplitude, and then in a cosine function. So V1 we have a negative 10 cosine omega t plus 50. Now we need to change negative to positive. So from negative to change to positive, negative or positive change to negative, it will be 180 degree. So I copy 10, I copy cosine, I copy omega t plus 50. But I change negative to negative 180 degree. So I have V1 equals to 10 cos omega t minus 130. Next, I change V2 from sine to cosine, and then I maintain positive polarity. So 12 I copy, sine I change cosine, omega t I copy, negative 10 I copy. When I change sine to cosine, it must be negative 90, as referring to here. So by adding up, I have V2 equals to 12 cosine omega t minus 100. And then I need to make sure this value is almost the same like this one. So what I need to do is I go to do some mathematics. I copy 12, I copy cosine, I copy omega t, but I want to make sure it is negative 130. So I copy negative 130 and I plus back my 30 degrees so that I can have negative 100 degree. And then we found that, okay, this omega t minus 30 are the same. But V2 has extra positive 30 degree, which means V2 will lead V1 because it is in plus 30 degree. If we change to cos omega t plus 230, we also can compare like this, which is the same. So, for example, calculate the phase angle between V1 equals to negative 10 cos omega t plus 50 and V2 equals to 12 sin omega t minus 10. So, we need to determine which is leading. Same as well, we need to convert into the same platform or the same cosine value, cosine function or sine function. Here, we change V1. Now, I have a V1 negative 10 cos omega t plus 50. So, I want to change to sine wave, sine function. First of all, I eliminate the negative. So, and then I change cos to sine function. It becomes 10 I copy, sine I change, omega t I copy, 50 I copy, and then from the negative and the cos function to sine function, it is negative 90 degree. So adding up, I have a 10 sine omega t minus 40, and I need to compare with omega t minus 10. So I copy 10, I copy sine, I copy omega t, I copy negative 10, and then I know that I'm still lacking of negative 30 to become negative 40. So from here, V1, I have same argument, omega t minus 10, but this is lagging. It is stay behind from V2. So we say that V2 is V1 is lagging of V1 lag V2 or V2 lead V1. If we put in we call the so-called vector diagram. So I know that my V1 is a 10 sine omega t minus 40. So it is here. And my V2 is a 12 sine omega t minus 10. Also, you can see V2 is the length V2 is longer than V1 because one is 12, one is 10. And then V2 is at a negative 10 degree here. And then V1 is at a negative 40, which is from here to here. And then we can see that V2 is leading V1. Next, phasor. When we talk about sinusoidal, phasor is a very good friend. So phasor is a complex number that represents the amplitude. Just now, when we talk about sinusoidal, it has amplitude, right? The peak value of the signal. And then we also have a phase of the sinusoidal, the omega t plus 10 minus 40 that is a phase. So just now it's quite complicated for us to learn. So we need to use a more familiar, easier way. So phasor is more convenient to work with than sine and cosine functions. It is introduced by Charles Steinmetz in 1893. Before we completely define a phasor, apply them to the circuit analysis, we need to be thoroughly familiar with the complex number. So we actually are changing the sinusoidal wave and a cosine wave into complex number. And then we can say that a complex number z can be written in a rectangular form. So actually complex number can be written in many forms. One is a rectangular form. What is rectangular form? It's like this. Z equals to x plus jy, where j is a square root of negative 1. It is not variables. X, y, z are variables, but j are a notation, which is referring as a square root of negative 1. And x is the real part of the z, y is the imaginary part of the z. The variables x and y do not represent a location. So the complex number z can be written in polar or exponential form. So we have three forms. One is a rectangular, one is a polar, one is an exponential form. Depends on your application. So for example, In polar form, z equals to r phi. In an exponential form, r equals to exponential j phi, where r is the magnitude of the z, phi is the phase of the z. As a summary, actually we can write our phasor or complex number inside this form. One is a rectangular form, one is a polar form, one is exponential form. Or z equals to x plus jy, z equals to r phi, z equals to r j phi. So we also can put in a drawing. For example, we have a real axis, we have an imaginary axis. I have my x, I have my y, then I get my z. So I can have my r, I can have my phi. So I can write like this: z equals to x plus jy, or z equals to r phi, Okay. So given x and y, we can get r and phi as below. So r equals to square root x squared plus y. We're using the Pythagoras theorem. If I say I want to find the r, actually is equals to square root of x squared plus y squared. And my phi is actually arctangent of y divided by x. If we know r and phi, we can also find our x value. For example, if I say I know my r, I know my phi, I want to find my x, just r times cos phi become my x. Or r times sin phi become my y. So in conclusion, z equals to x plus jy, or equals to r phi, or equals to r cos phi plus j sin phi. So addition and subtraction of a complex number are better performed in the rectangular form. Multiplication and division are better done in the polar form. This is the basic properties of complex numbers. So for example, if let's say I have a z equals to x plus jy, or equals to r phi, and for example, I have a z1 equals to x1 plus j1 equals to r1 phi 1 and 2. Then I add up together z1 plus z2. It becomes x1 plus x2 plus I factorize j, and then I find j1 y1 plus y2 like this. If I subtract, means z1 minus z2, this one. So I use x1 minus x2 plus j. I factor the j, y1 minus y2. For multiplication, x1 times x2, we use a polar form. So which is r1 times r2 and phi 1 plus phi 2. Division as well, z1 divided by z2, r1 will be divided by r2. At the same time, my phi 1 will minus phi 2. Reciprocal, 1 over j is actually negative j. 1 over z equals to 1 over r, and then negative phi. Square root of the z equals to square root of r, and this one is not really okay. And then complex conjugate. Conjugate means if let's say I have a z equals to x plus jy, I conjugate the z, it becomes x minus jy. Or r equals to r negative phi, or r exponential negative j phi. It depends on what application we want to use. Then we will choose the appropriate complex number formation to do the additional, subtraction, multiplication, and division. So the phasor. The idea of the phasor represented is based on the Euler identities. So we have exponential of plus minus j phi. We also can represent it equals to cos phi plus minus j phi. Cos theta equals the real part of the exponential j phi. Sin theta equals to imaginary part of exponential j phi. And then it can be written like this, or we write as re as a real part of, imaginary is imaginary part of. So no worry, this is just an introduction for you. What is a phasor diagrams? What is a a phasor? What is a phasor? What is a complex number? So for example, I have a now we try to put in application wise. If I have a voltage Vt equals to Vm times cos omega t plus theta, we can write in a phasor form. So we can write like this: real Vm exponential j omega t plus theta. Or we can write this, or like this. And then we know that this is V equals to Vm exponential j phi, or Vm angle of phi. V is thus the phasor representation of the sinusoidal of V. Equation 9.220a or equation 9.20b can be used to develop a phasor, but the standard convention is use equation 9.20a. You see, actually our sinusoidal waveform is actually a circle. Why I say so is, even though so many cycles turn over, it is only just turning around the circles. So for example, this equation, Vt equals the real part of the Vm exponential j omega t. So the value is actually fluctuating, but we can see that the magnitude is the same as the cycle. And then we have a angle, we have the magnitude, which is in the real part and imaginary part. It has a frequency. It also has a rotational frequency. So we can put in like this. This is called time domain representation. You can see this is time. This is time domain representation. This is phasor domain representation, where we have a angle. So time domain, we have a Vm cos omega t plus phi. We also can represent it in a phasor domain, where Vm angle of a phi. So which is more simpler. And sinusoidal phasor transformation, we can transform, for example, Vm cos omega t plus phi, we can transform like this. Or when we have a sine, we transform like this. Im cos, Im like this. Im sine, we have Im like this. So for the phasor domain, we no more deal with the cos or sine function. And then a phasor diagram can be plotted. For example, we have Vm equals to Vm angle of phi, Im equals to Im of a negative of theta. So I have a real axis, I have an imaginary axis. This is my Vm. Okay, this is my Vm. This is my V vector. This is my length of the Vm. And then it is positive angle. So we need to draw like this. And then we need to assume all the rotational angle will be go through anticlockwise. Anticlockwise. Then I know that my our Im is actually in negative plane. So I found that my I is here. My length of the I is Im. Then it is in negative theta. So as overall, this is phasor diagram. So how can we know that it is a leading direction or lagging direction? The most simple way is we need to standing. We need to stand still and see which one comes first. For example, if let's say I stand here in the laser pointer mark. So which one will I see first? V, right? I will see the V first. After that, I will come the other side. When we stand still, we need to know actually the rotation will be in anti-clockwise. Just for your information, clockwise rotation will be positive direction. So if I stand still here, I will see Vm come to me first, and then I will come later. So V will lead I. Okay. Let's have a look on the example. If let's say I want to use 40 magnitude angle of 50 degree plus a 20 magnitude of negative 30 degree and a square root 8, what should I do is using polar to rectangular transformation. So I transform this polar to rectangular first because it is a additive function. Then I transform 20 to become like this, and I add up together. Then I transform back to polar. So this is my, and then I'm taking the square root of this. Then I found this one. So I transform to the polar. I'm taking square root and found this one. B. So I have an extraction. So I change to rectangular form. Okay, I change to rectangular form at the top, and then I do this is conjugate. Conjugate means negative become positive. So multiplication will be in polar form. So I found that the final answer will be like this. Actually, we can just use a calculator to calculate it. This is just for your information that additional and a subtraction, we try to use a rectangular form. Multiplication and division, we try to use a polar form. So another example, we direct, for example, we try to direct apply in our circuit problems. So I equals to 6 cos 50 t minus 40 degree. So we have a phasor I, so I copy 6. This is cos, I just put an angle, then this is minus 40 degree. Okay, so phasor form. Yeah. So V and the amplitude here is negative, so I need to change into positive. And then this is sine, I need to change into cos. So first, I want to eliminate the negative and sine become cos. So I copy 4, I change to cos, I copy 30t, I copy plus 50, and then I know that the changes take place by plus 90 degree. So pop up, I have this one. Then we change the phasor diagram. V equals to 4, cos is the angle, plus 140 degrees this one. So for another example, we want to find a sinusoid represented by this phasor. That means we want to convert this sinusoid into a instantaneous one. So I equals negative plus j4, we can put in a polar form like this. Use calculator. Then we can transform to the time domain. So I copy 5. I remember it's a time domain. We need to have a time. I copy 5. Angle is cos. 126.87 I copy. Then I know that I need to input omega t plus. Okay? This is so easy. Then another one, Vm equals to J8 exponential J. Same as well. I know that my J is this 1 over 90 degree. I need to eliminate the negative first. Or not eliminate, I just bring forward. For example, I copy my J8. And then I know that exponential is an angle. Then I directly copy negative 20 here. And then from here, I convert into without J form. So how can I convert is, I know that J is 190 degree. So I copy 190 degree. And then I copy my 8 and negative 20 degree. Then I do the multiplication. So 1 times 8, 8. 90 minus 20 become like this. And then I change it to time domain. So I copy 8. I copy the angle into cos. I copy plus 70 degree. Then I add omega t. So given this is a direct application in our electric circuit. So for example, given IT equals to 4 cos omega t plus 30 degree and IT equals to 5 sin omega t minus 30 degree, we need to find their sum. Means I want to add up I1 plus I2. So when we deal with a summation, what we need to do is we need to convert into rectangular form. Then we add up together. So first of all, I need to convert into polar form. So I copy 4. Cos is an angle. Then copy 30. Done. Then this is sine. I need to convert into cos. So I2 I copy. Phi I copy. Sine I convert to cos. Omega t minus 20 I copy. When I convert sine to the cos, I need to add negative 90. So as overall, I have this one. Then when I convert to the polar form, phi I copy. Cos is angle. Then this is negative 110. And we let I equals to I1 plus I2, where equals to I. You see, this is boats. Boats means it is a vector. This is actually a vector. It has a direction. So I1 plus I2. So I use I1 430 plus phi 30. Phi negative 10, 110. Then I convert both of them into rectangular form. So real part plus real part, imaginary part plus imaginary part. I have my rectangular form. Then I convert back into polar form. After that, I convert back into time domain. This is not time domain because we don't see time. This is time domain because I see IT. We saw the T. So I copy 3.218. Angle will be my cos. I copy negative 56.97. then I add omega t. Okay?